Welcome to The Explainer. Today, we're conducting a clinical autopsy. Our subject, a rigorous, deeply elegant, and ultimately failed proof of the most notorious trap in mathematics, the Collatz Conjecture. Our goal here isn't just to look at the math. We are going to isolate the exact structural breakdown where strict logic hits an insurmountable barrier and collapses into circularity. We want to see exactly where human reasoning meets its absolute limit. Take the number 27. Deceptively simple, right? Yet, under the rules we're about to explore, this number doesn't just go quietly into the night. It explodes. It traces out a chaotic 111-step sequence, climbing to a towering peak of 9,232 before it finally exhausts itself and plummets back down to 1. This explosive, unpredictable path is our hook into the trap. It shows how something incredibly basic can harbor immense complexity. The strict, foundational rules governing this trap are aggressively simple. It's almost like a child's game. You take any positive integer n. If n is even, you cut it in half. If n is odd, you multiply it by 3 and add 1. Repeating these two basic arithmetic operations is supposed to eventually transform every single positive integer into the number 1, permanently trapping it in an infinite 4-to-1 loop. That is the conjecture. Simple to state, completely impossible to prove. Pushing numbers forward through this map generates what mathematicians call hailstone numbers. The sequences rise and fall with violent unpredictability, creating these chaotic, fractal-like trajectories. Massive computational networks have verified that every number up to 2.95 times 10 to the 20th power eventually falls to 1. That's quintillions of numbers. But remember, in mathematics, checking quintillions of examples is merely observation. It absolutely isn't a rigorous proof. Infinity is much bigger than any number a computer can check. To solve a problem of infinite forward chaos, modern analysts demand a structural shift. If pushing numbers forward yields these unpredictable hailstone storms, we have to invert the mechanism. Our analysis moves from generating forward chaos to tracing the reverse operations backward. Instead of watching numbers fall, we're going to hunt for the roots. We are essentially reversing the flow of time. By mapping the inverse operations, the chaotic downward webs actually morph into a perfectly structured upward branching organic vector tree, and this tree is rooted firmly at the number 1. The hypothesis driving this proof attempt is brilliant in its simplicity. If we build this tree upwards to infinity, it will eventually connect to and encapsulate every single natural number. Every number should be a leaf on this massive tree. This tree doesn't just grow randomly, it's dictated by an exact inverse algebraic formula. From any node n to find its parent, we just reverse the operations. The previous step was definitively 2n. But if the number satisfies a specific modular constraint, specifically if n-1 divided by 3 yields an odd integer, it also generates a second odd branch. This strict formula is what controls how the tree grows backward, giving us a perfect map of the system. Structurally, this entire tree relies on two distinct mechanisms. First, we have infinite even doubling. Every single node infinitely generates a straight vertical doubling branch, 2, 4, 8, 16, and so on. The second mechanism is conditional odd branching. Because of strict modulo arithmetic, these odd branches are sparse. They only sprout when mathematically permitted, creating a vast but highly regulated asymmetric canopy. It's an intricate balance of predictable doubling and conditional splitting. To rigorously prove this canopy covers all integers, researchers deploy a proof by contradiction using the well-ordering principle. They start by assuming the conjecture is false, meaning some numbers out there never reach 1. From that hypothetical set of escaping numbers, we introduce the variable e. E is defined as the absolute minimal counterexample. It's the smallest possible integer in the universe that breaks the rules and escapes the tree. If we can prove that this absolute smallest counterexample, e, mathematically cannot exist, then the entire conjecture is proven true. The logic is airtight. If the smallest escapee can't exist, no escapee can exist. But the formal attempt to prove this requires us to test both logical pathways. Pathway 1. The minimal counterexample, e, is an even number, and pathway 2, e, is an odd number. We have to shut down both doors. Watch how quickly case 1 collapses under its own logic. If we assume our minimal counterexample e is an even number, we simply apply the foundational Collatz rule. Its immediate next step has to be e divided by 2. That's just the unbending rule for even numbers. Look at the magnitude here. Because e divided by 2 is strictly smaller than e, its trajectory cleanly drops below the line of e. But remember our foundational definition. E was defined as the absolute smallest possible counterexample. If e over 2 is smaller, it can't be a counterexample. It must eventually reach 1. And if e over 2 reaches 1, then e itself reaches 1. This is an immediate contradiction. Case 1 is dead. E simply cannot be even. This logical elimination corners us entirely into case 2. The minimal counterexample, e absolutely must be odd. And here is where the mathematical calculation sharply shifts. Because e is odd, the forward mapping rule requires us to calculate 3e plus 1. This single operation completely changes the trajectory. The calculation, 3e plus 1, sharply scales upward. It shoots completely off the top of our minimality frontier, becoming strictly greater than e. And this upward leap? This is exactly where the rigorous proof encounters a devastating, insurmountable structural obstruction. We lose our grip on the number's size relative to our starting point. Here is the exact point of failure. Because the infinite inverse tree is only partially ordered by magnitude, the pads don't strictly increase or decrease. Therefore, 3e plus 1 can exist completely outside the tree without ever violating the minimality of e. This upward leap completely destroys the proof. The successor, 3e plus 1, is free to belong to an entirely separate, isolated loop, or it could diverge to infinity, without ever contradicting the fact that e was the absolute smallest number to escape. This brings us to the honest accounting of our autopsy. We're left with two conflicting realities. On one hand, we have rigorous truths. The algebraic inverse mapping does build perfect, non-overlapping trees, and any minimal counterexample absolutely must be odd. But on the other hand, we've exposed an irreconcilable gap. The logic breaks into circularity because it cannot account for the magnitude barrier breached by the 3e plus 1 operation. We are stuck. Let's summarize the forensic breakdown. The inverse mapping strategy successfully translates chaos into perfect algebraic trees. We've definitively established that if a counterexample e exists, it must be odd. However, the odd calculation mathematically forces the value upward. This scaling violently bypasses the minimality frontier, rendering standard proof-by-contradiction methods entirely powerless. The pure logic simply cannot constrain the sequence's escape once it jumps. This is exactly why the Collatz conjecture remains the most dangerous, unsolved problem in mathematics. The inverse tree is mathematically beautiful, but structurally incomplete. The tools of pure logic hit a wall. We are left with the ultimate, lingering question for the next generation of mathematical pioneers. Does every number eventually reach 1, or is there an e waiting in the dark, ascending into an infinite, undiscovered canopy?